Hey everybody, this is Mrs. Levin and I'm here to introduce Chapter 16, all about reaction energy, which essentially is our study of thermochemistry. If chemistry is the study of matter and the changes that they undergo, thermochemistry is going to study the energy changes that accompany all of those other kinds of changes. And we briefly introduced this way back in chapter 2 in the beginning of the year, where we started to talk about calorimeters and we started to talk about those different types of physical properties. Okay, so we used a styrofoam cup calorimeter. This here is a picture of a bomb calorimeter, which is not actually making a bomb, but is the name for the reaction chamber, so that you can see what the difference in energy is going to be. You can have simple soda can calorimeters or even test tube calorimeters, so that you're basically just figuring out how much energy the water inside your calorimeter is going to absorb. All right, and that's going to tell us a lot of information about the substance that you're studying. All right, so this is a review slide. You've seen this before, but we measure our heat energy through calories. All right, and a calorie is the quantity of heat that raises the temperature of water, 1 gram of water by 1 degree Celsius. So we have to be very careful because this definition for calorie is very similar to specific heat. Our American diets are based on a 2,000 calorie diet, and notice that is a capital C and this is a lowercase c because 1 calorie is 1,000 of these calories, but Americans tend to flip out if they see the word kilo with something, so that would be our kcals. That's what this thing is. This is actually a kcal, so this is 130,000 of those calories. Okay? So in the scientific community, we end up using joules, Joule, okay? And we know that a joule is about a quarter of a calorie, but the conversion factor that we use, and we'll see our number appear again, is 4.184 joules is equal to 1 calorie of energy. All right, so specific heat has that similar definition to calories, but the specific heat is going to be a physical property where you can figure out how much energy it takes to heat 1 gram of the substance by 1 degree Celsius. All right, the definition for calorie is going to all be about water. All right, and specific heat is going to be about the substance. So I like to remember that the C and C for specific heat for substance, where calorie doesn't have, there's no C in the word water. So we see our Q equals MC delta T equation again, MCAT. So this is our heat quantity and the mass of our substance and the specific heat and the temperature change that we see. Delta T is again TF minus TI. This should be a review for everyone. And you can rearrange our equation to solve for C by using C equals Q over M delta T. Make sure that you put the denominator in parentheses because we want to make sure that we're dividing by the product of those two numbers. All right, in other countries, and as you can see from the poster that was in my room, I've been to 23 other countries, and the other countries don't report things in calories. If they do, it says kcals, but they report it in kilojoules. So you'll see these kilojoule labels on a variety of different things. And that's because, unfortunately, America is a little bit behind the curve when it comes to our use of the metric system. Okay, some important values that, again, our review are going to be our specific heat of water, of ice, and of steam. Okay, 4.184 joules per gram degree Celsius versus 2.03 and 2.01. That's why it is always hotter down by the water. No, it is always cooler by the water at the beach, because that is going to take way more energy than, say, the silicon dioxide is here, because water has this specific heat of 4.184, and silicon dioxide is going to have something of, like, I think it's 0.9-ish, which is like really, really, really low. So it's going to have much hotter sand than it is going to have water. All right. So, what this brings us to is then talking about how energy is going to be measured in a reaction. And one of the big words that you're going to see use this chapter is enthalpy. Okay, enthalpy is going to be the energy associated with it. Okay, so this means the same thing. Delta H is our change in enthalpy, which is the same thing as our Q. So you can actually rewrite the delta H equals mc delta T equation. Why aren't they using the word heat? Because heat has this connotation that it's going to be hot. All right, and we're not always going to get hot. Sometimes things are going to get cold, and you want to make sure that you don't have this preconceived notion that you are looking for the heat of a system. Okay, so when it comes to our enthalpies, we can either have exo or endothermic. Okay, exo means to exit or exterior. Endo means to enter or to come in. So in an exothermic reaction, you are going to see heat leave the system. So it's going to be a product. Whereas an endothermic reaction, you are going to need heat energy or um, your quantities to enter. It's going to be a reactant, and you're going to need that in order for the reaction to actually happen. Like melting ice is an endothermic reaction. It requires energy. All right, so we're going to see these in thermochemical equations. So you have your regular equation, but it also has the quantity of heat that is either released or absorbed written on one side or the other. It totally depends on what the reaction is. So if you are going to make water, water is a naturally occurring substance, it is going to release 241.8 kilojoules of energy. Whereas if you want to break up chalk into calcium oxide and CO2, this is our special decomposition reaction of a metal carbonate, ding, 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 it is going to require 177.8 kilojoules of heat. All right, so we definitely see a difference there. All right, so let's compare and contrast these two. All right, so when it comes to an exothermic reaction, our energy is released. Exo means to exit. It is going to be a product. All right, and you are going to see that our delta H is going to be negative because the products are going to have less energy than the reactants. So if the reactants start up here, this is our simple energy diagram. So we have energy as our y-axis. Our reaction coordinate is a fancy word for time. And our products are going to have much less energy than that. So if you have this energy and then this is where you end, okay, if you compare these two values, the delta H will have dropped, which means it is going to be a negative value. So you'll see that the delta H over here is going to be negative 483 kilojoules. That negative tells you that it is going to be exothermic. So what do you suppose is going to happen with our endothermic? That's right, people. You are smarty pants. You know that an endothermic, where heat or energy enters the system, is absorbed. So the products are going to have more energy than the reactants. So our delta H is going to be positive. So if we have our reactants here and our products here, and we take a difference in those energies, we're going to see an increase. And you're going to see that the products are going to have way more energy than the reactants. So our delta H is indeed going to be positive. If you want to break apart water, like in the electrolysis that we saw, okay, we need to add in this energy in order for it to break up into our H2 and O2, like you saw in that Hoffman apparatus that I did back in our uh, chemical reactions problems. All right, so when you write a thermochemical reaction, you got to know if it's endo or exo and what side you put it on. So here it says 1 mole of carbon and 2 moles of sulfur makes 1 mole of carbon disulfide. Carbon plus 2 sulfurs make carbon disulfide, CS2. It has a positive 89.3 kilojoules of heat enthalpy. So if it's positive, it's going to be endo, and it enters the system. So I'm going to use 89.3 kilojoules, and voila, there is my thermochemical reaction. Okay, so you end up seeing, it doesn't matter if you write it first or in the middle, but typically it's either in the beginning or right before the yield sign. But there you go. There's your endothermic reaction. Okay, so what if you end up seeing this, where you have 2 moles of hydrogen and 1 mole of oxygen to make 2 moles of water? H2 plus O2 make 2H2O. Now, it's going to have a delta H of negative 483.6 kilojoules. Negative values means it is exothermic, so I'm going to have it exit the system. I am going to add it over here. Notice, big thing to notice. This and this are 2 different signs. Exothermic just means that you put it on the right side. You don't make negative energy. That negative sign is just going to tell you where to put your delta H value. Okay, that's all that it does. The negative sign only tells you what side of the equation to put the value in. It is not negative. I do not want to see any negative signs there. This plus means and. This doesn't mean necessarily a positive value. 2 moles of hydrogen and 1 mole of oxygen react to make 2 moles of water and 483.6 kilojoules of energy. Okay, examples of these endo and exothermic reactions are going to be things like our instant hot packs and instant cold packs. So our endothermic is our ammonium nitrate. So you're going to see that it's going to require energy in order to go into solution. That's a chemical reaction that you do when you pop or break it. They used to sell these when I was a kid, and actually when my dad was in the hospital and he broke his hip, to give him some relief from the pain, they used these instant hot packs, which is basically going to be the dissolution of the calcium chloride or magnesium sulfate. They discontinued them in like real like CVS's and stuff like that because people were burning themselves. Okay, but you'll see that their energies are going to be products on the right-hand side. The hand warmers that you use and foot warmers when you go to like tailgates and football games and stuff, that's just powdered oxygen, or sorry, powdered iron, which is going to react with the oxygen. There's no breaking of anything, so you're basically harnessing the power of rust. Imagine that. And that is going to be what we see for heat. Okay, so those are our thermochemical reactions.